Okay, I want to start with an example out of your assignments from the other day. I don't know if you guys recall this example, but I might have asked you to do something like this. Let's say that y was actually let's change it. Let's say that f of x was supposed to be x squared. Okay, suppose this is an example I give you here. And let's say that I tell you that g of x is supposed to be x plus 1. If I were to ask you for f of g of x, could you guys tell me what that is? So given these parameters, f of x is x squared, g of x is x plus 1. Can you tell me what g of x is?
X plus 1 all squared? Nope. Yep.
Yeah, x plus 1 all squared. Because really what I'm asking you to do is take this and plug it inside there and make it that. So far, so good? What if I were to ask you for g of f of x? Okay. Now, in both of these cases here, you have to take x squared and add 1, but order matters. And on the assignment, oh goodness, I'm never going to start. Okay, on the assignment, I gave you guys a question about taxes and deductions. You guys recall this one? Where there is a very big difference between subtracting 300 and then doing 29% tax versus the other way around, right? And the same thing applies right here. My goal today and tomorrow is to talk about how we can kind of understand these differences right here and kind of get a visualization of what's going to happen on a graph. Like, how will these things change? I'll give you an example here. Well, what does an x squared graph look like? Well, it's your basic parabola, right? I'll even grab a graphic calculator here just to speed things up. There's x squared, your basic parabola, right? How does the graph change as I compile functions together? We just want to look at how things are going to transform, hence the topic of the day. So I'm going to do a second one on here. I'll do it in dark ink, like use this thing here. So what if I do x plus 1 and I square it? How does it change the graph? It's the exact same shape. It's got the exact same parameters. Like, these things are complete. It's not a mirror image of each other. If I use the word translation, would that make sense? Right? Like, this graph has been literally taken, picked up, and it's been moved that way. It's just been slid over. That makes sense so far? Now, I want to point something out here. That was where I put an x plus 1 inside the function. X plus 1 is now inside my square function, and that caused it to move that way. How far did my graph move? Well, it looks like it moved 1 unit over. You get what I'm saying? Then I'm just going to do a quick test here. What if it wasn't x plus 1? What if it was x plus 2? Well, now there's my original. There's my new graph, and can you see how it's been moved over 2 units? What if I were to change it, and rather than it being x plus 2, what if I made it x minus 5? I want to take a shot at what's going to happen. It's going to go 5 that way. And mathematicians picked up on this pattern pretty quickly and said, hang on a sec here. I'm starting to recognize what's happening here. It's got the same basic shape to it, but we've transformed it. In this case, we've translated it around the graph. So I want to point out that when we put a function inside another function, like say the x plus 1 went inside the squared function, it moved it side to side. Makes sense? Well, what happens if I take the plus 1 though, and I put it after the x squared function, right? See, when the order mattered, here we added 1, then we squared. What happens if I square first and then add 1? And so, again, I'm just going to kind of explore this. What if I were to do x squared and then add 1 after? And maybe you already kind of figured this out in your head what will happen, but what occurred there? Yeah, it moved up 1. And I know it's kind of hard to see just because of them blurring on top of each other, but what do you think is going to happen if I subtract 8 afterwards? Yeah, it's going to basically have the same shapes as each other, only it's going to be down 8. Now, I know it looks like they're not exactly the same as each other, but that's just because this graph right here, we don't actually keep drawing it further and further up, if that makes sense. Like, if I could, how do I do this? File, screenshot. There. Okay. You know how it doesn't really look like they have the same shape to them, right? But if I could cut just this section out right here, just from there to there, and pick it up and move it down there. You get what I'm saying? Like, it actually is the same. It's just this graph keeps going, but this one stopped due to my upper limit parameters. If I can keep this one going right here, hopefully you'd agree that they actually are the same as each other. So back to my point here. Order matters. Let's get rid of you. If I replaced x with x plus 1 inside the function, things went left and right. But if I replaced the outside and I added a function outside and we went up and down, that's almost like it was outside the function. Does that make sense so far? That's my goal today, is we're going to talk about two things. We're going to talk about what happens if you take a function and you replace something inside of that function. How does it affect it? But then we're also going to talk about, well, what happens if you were to modify after the function is over? And you'll notice that things usually happen either in a left-right point of view or an up-down point of view. So why don't I start now with the actual example I wanted to begin with. Let's try this one here. Let's compare the graph of x to the 3 and then y equals, pardon me, x minus 1 cubed plus 3. Using what I've shown you before, let's not even graph it yet. Let's just talk about the two modifications we have. This plus 3, you guys see that's a modification we've made, right? Is that plus 3 after the cubing function is over or before? Okay. So based on what we think we learned, what's that going to do? Is it going to move things in an up-down direction or side-to-side? Up-down, yeah. Take a guess. What do you think it's going to do if it's a plus 3? Let's move up 3, yeah. So I think it's going to move up 3. This is opposite, not opposite, but it's in contrast to, see how this minus 1, though, is within the cubing function, right? The original function we had here was a cube function. This one right here, before we cube, we're going to subtract 1. Now, you know how roots and factors are opposites of each other? This is kind of the same thing, right? Like, if this thing right here was a factor, what would its root be? Well, if the factor was x minus 1, the root would be plus 1. That same sort of kind of logic applies in terms of this. So even though you see a minus 1, this is actually going to move in the positive direction 1 unit. So the positive direction would be to go this way 1 unit. It seems kind of backwards. But just think of how factoring and roots are opposite of each other. And so now I'll just prove it to you. Let's see whether our intuition makes sense. So here's the original function, x to the 3rd. And then I'm going to do two things. Before I cube the x to the 3rd, I'm going to subtract 1. And then after I'm done cubing it, I add 3. And that terminology is so important. One of them is before I apply the function, because the function is to cube stuff, right? But then the other thing is, after I'm done, then I can do other stuff. And as we take a look at it, here's the first one. That's a cube graph. Here's our second one. Now it's kind of hard to see exactly where they are, but maybe I'll try doing this thing again, actually. Drag it into here. That's really cool. I've never tried that before. Okay. One really key point to maybe focus on is the original graph went right through the origin right here, right? Where did it move to? I believe it's right there now. Can you guys see that one of the graphs used to look like this in green? And then this graph is slightly moved over, but it's now sitting right here. This coordinate point has been moved up 3 and over 1. See how that works there? I know it's kind of a jumbled mess in there, but this point right here has been over 3 up 1. And really all of those points have. Hey. He's in the classroom right over there, the Brant's classroom. So. Okay, I want to give you guys an analogy, because you guys know I love doing analogies. Imagine that you need to go to, say, the bank, and the bank is going to be your function. And so the bank can do a lot of things. I mean, this analogy breaks down sometimes, but let's say that you're going to go to the bank, and the bank is going to square your money. Okay, that's the function. It would be awesome if this happened. Okay. So there's two ways this could happen. Option one, you were going to square your money. But what happens if before you went, you added $1? What would that do? Well, let's say you went to the bank with $2. Okay, you were going to take 2 and turn it into 4. That makes sense. But what if you started with 2 now? You wouldn't actually get 4 because 2 would add 1 more to it. You'd actually have 3, and then when you square, you'd have 9. So I just want to show you this idea. Originally, if you started with 2, it would have given you 4. But under this condition right now, what happens? Well, 2 now gives you 9. Does that make sense? Because it's almost like you picked up a free dollar along the way. Okay, now, in this analogy here, let's say that you actually only wanted $4 though, right? Let's say that your goal was to have $4. You now have too much. You know, one thing you could do is you could intentionally bring one less dollar. It's almost like you know that you're going to find a random dollar lying on the street. So rather than bringing $2, why don't you just bring $1? Makes sense? Because you're going to bring the dollar that you're expecting to find. You're going to bring the dollar that you are expecting to find. You're going to find a free dollar sitting somewhere. And then when you square it, you'll get 4. And so although you could argue that 2, 4 turned into 2, 9, sometimes it works better to say that maybe what happened is you started with 2 and were expecting 4, but now you actually only need 1 to expect 4. I'll talk about where those points lie on a graph. 2, 4 would have been, say, right here. 1, 4 would be right here. What happened to that point? It got shifted that way by 1 unit. Which is kind of what I've been kind of showing you before, right? Let me do an opposite example. Let's say that it was x minus 1 squared. In this example here, there's a bully. And this bully always steals $1 from you. You know this every day, right? And so you normally were going to bring $2, and your $2 would have turned into 4. But before you can get to the bank, this is really a key part. Before you get to the bank, the bully steals one of your dollars. Well, if it was going to be 2 for 4, now if you bring 2, you're only going to make 1. See the problem here? So how would you compensate in this example here? Before you get to the bank, should you bring $2? How much should you bring? Bring 3, right? Because if you brought 3, you want to end up with 4 when you're done, right? If you brought 3, you're counting on getting stolen money from. Right? So your 3 turns back into 2, and then it does turn into 4. Right? So in this example right here, if you do x minus 1 squared, it actually causes this point at 2, 4 to go over here to 3, 4. So this would be like before you get to the bank kind of functions. And it seems opposite. If you see a minus sign, it actually means that you need to add 1 more. Right? Because before you start, someone's going to steal your stuff. So bring an extra 1. Whereas if you see a plus sign, it means you need to bring less. So if you were to see, for example, let's say f of x was x squared, that just works there. And let's say that you were to do g of x, and it was x plus 5, and I were to ask you to do f of g of x, this means x plus 5 squared. So far? What's happened from this graph to this graph? Which way did it move? If the original graph was right here, where did this graph move? To the left by 5. In a way, this example here is you're picking up 5 extra free dollars, right? So bring 5 less, right? You're going to get 5 more free dollars before you get there. So bring 5 less. 5 less means go this way by 5. So if you wanted to make 25, right, if you wanted to make $25, you were supposed to bring 5. But under this new example here, if you want to make $25, bring nothing. I know the example's not perfect. Does that make sense so far, though? Okay, let me try the opposite. What if I were to give you this one right here? I'll still use the same 2 functions I had, which were f of x. I'll just erase, actually. It makes more sense. But what if I were to change this up and do g of f of x? Now here the order is a bit different. Here you're going to take your money and square it, and then when you're done, you're going to add 5. So this is not the bully that robs you before you get to the bank, and this isn't you finding money before you get to the bank. This is afterwards. Right? Now you guys can kind of imagine a real life scenario. Sometimes it'd be better to put the money in before than after, right? Sometimes it's like think stock market. If the price of something is going to double, like all of a sudden stock X is going to rage through the roof, would you rather have your money invested in that stock before or after? Well, before, right? Because if you can get your money in before it doubles, then your money doubles. If you get it in afterwards, well, hopefully it'll still grow, but you don't know. See the difference there? That's what's happening right here. Here, we're going to square your money, and then when we're done, we're going to add 5. So let's talk about some examples. Let's say you brought $2 in this case here too. $2 originally up here would have given you 4. Here, $2 is going to give you 9, right? Because it would give you the 4, and then when you're done, you get 5 more. You know what this does right here? It affects the Y value. The Y value just becomes bigger. Your output becomes bigger. In examples where it's like after the function, it affects your Y values because your output is different. But in this example right here, wherever the heck I was drawing, see where you get to add 1 or subtract 1 before you start? That affects your input. Here, you need to bring a little less money. Here, you need to bring a little more money. So your input is changed. But if I were to do almost the exact same thing, but throw the number on the outside, now your output is changed. Once you get a hang of these patterns, you can start to see how graphs are going to be affected. So, okay, let me walk through my notes, because obviously I make notes for a reason. But hopefully that kind of gives you a preamble to start. So let's talk about some of the things we've seen in these examples. Vertical translations. Let's say I were to give you a graph of y equals f of x. And then, hopefully this is clear. This is after you're done doing the function. See how after that you're adding k? Well, this is congruent. You guys know what congruent means? Like, looks the same as, only shifted maybe? Congruent to the graph of y equals f of x. All you're doing is you're moving the graph up or down. Moving it up or down because your output values have been changed. Right? You started with 2, you're supposed to make 4. Hey, $5 free bucks, now I have 9. Right? But it was after the function occurred. So if it's positive, go up. If it's negative, go down. And I've underlined this word right here. Vertical translations happen after a function. Right? After whatever the function was supposed to be, then you move the graph up or down. So it only affects the y-coordinates. Here's a way that you can write it. You can actually write it rather than y equals f of x plus k. You could also write it as y minus k equals f of x. See how I'm like pulling the k to the other side, making it negative? Or here's another way of looking at it. You were supposed to start with x, like in my example 2, and it was going to make 4. Well, now 2 makes 4 plus 5 more for 9. So the x values stay the same, the y value is the one that changes. So that's what happens in the outside the function examples. So let's try a quick one here. What's going to happen to these two graphs? Could you be able to sketch it real quick without a calculator? What does an x squared graph look like? It's your basic parabola, right? What's x squared plus 3 going to look like? Just 3 up, right? And I mean, we know other things, right? Like that plus 3 is the y-intercept. So, I mean, that kind of makes sense. You know, basically, it's just the exact same graph, only 3 higher. This is actually really useful because now you can get like a picture of what a graph looks like in your mind without having to like fully graph it on the calculator, because you kind of get a sense of, well, this is where it should be now. Right? All you've done is you've taken a basic graph, moved it up 3. Okay, well then horizontally is the kind of the other side of the coin. This is where you can see, like, rather than writing f of x, I'm writing f bracket x minus h. I'm doing something to the input before I start. So either I'm stealing money before you get to the bank, or I'm giving you more money before you get to the bank. You know what I'm saying here? Like, the input gets to change. Right? All this does is slide the graph left or right. And I'll skip through these notes here, because I think you guys get the concept. What happens here? You got x squared and x minus 3 squared. What's happening? Which way does it go? Yeah, and it just, all you got to do is make sure that it's backwards. If you see a negative, okay, first of all, you guys know how factors and roots are opposites, right? So if you see x minus 3, your root is 3. Right? All it means is that rather than your graph being here, where your root was at 0, now your root is over here at 3. So that's one way you could approach it, is saying, well, I know what this guy's root is going to be. Right? But here's another way of approaching it. You were going to start with an unknown amount of money. Here, that same amount of money you're going to bring, you're getting robbed by $3. So what should you do? Bring $3 more to compensate for it. So for example, right here was the 0.11. Well, if you bring $1 right here, that doesn't work out for you, right? How much money should you actually bring here to compensate for that? Bring 4. Because then 4 minus 3 would give you 1 right here, and then 1 squared would give you 1. See how that works? This 0.11 moved over here to 4, 1. This point right here moved to there. This point right here moved to there. So I don't know if that analogy makes sense, but you're going to get robbed. Well, bring more, right? Bringing more means make your x values be higher in advance. So, long story short, negatives go this way, positives go this way. So let's try some tasks here now, just to make sure we've got the concept here. Which way do all these graphs move? So x minus 6 moves to the, yep, x plus 3, f of x then minus 6, good, and then f of x add 3 afterwards. Cool. Does that make sense to all of you? Now the challenge ones. What if I just mess around with the algebra a little bit, just to, you know what I mean? What's happening right here?
Left.
Up. So this plus 4 right here, you need to add 4 to the other side, but you have to add 4 after your function is over. You can't like add 4 inside, and I don't know what your function is. The function could be a quadratic, a cubic, absolute value. Does that make sense? But if you have a number on the other side, it has to be like outside of whatever your function was, right? Like let's say it was y minus 4 equaled x to the 5. Say that was your function. Well, then it's going to have to be y equals x to the 5 plus 4. See this thing right here? It's not inside, and that's it. And then by that logic, this one right here is going down. Sound good? Okay, I found some pictures here. Very likely on the diploma, they'll give you some diagrams to look at, and they'll ask you to try to figure out how one function turned into another. So what they'll often do is they won't give you an equation you can type in your calculator, because otherwise you'd be able to use your calculator too much. They might just say, if this is f of x, what is this one here? And so I'll just tell you what the right answer is first, and you guys can see whether it makes sense to you. This would be f of x minus 3. Does that make sense to everybody? If this is f of x right here, this is f of x minus 3, the dotted one, because it got moved over 3. And then x minus 3, if you use x minus 3, it sends it that way. So let me try one more. I'm sure you guys will race ahead of me here. Let's say this one is g of x. Then what's the dotted one here? But after the brackets, because it's going down. Okay, can we do one of each? Sure, why not? Let's call this one h of x. What's happening here? It looks like it's going up 1 and over 1.5 maybe? So, how do I get it to go up 1? Okay, add 1 after the brackets, okay. Now I need to get it to go to my left by, I think, let's call it 3 over 2, 1.5. So how do I do that? Yeah, add, because add actually makes things go that way. And once you wrap your head around it, as soon as you memorize these rules, you don't have to think as much about it. And then let's do one more, A, F, G, H, I, sure, I of x. Okay, so it looks like this one goes down by 1. So I'm going to add, subtract 1 at the very end. And I believe it's going over by about 1/2. So x minus 1/2. Makes sense, everybody? You guys good? Okay. Well, I'm just doing a lot of different tasks on the same concept here then. So if I were to ask you then to put this into words, there's another thing they could assess you on. It's like, what's the vocabulary you might use? So here's the terms you might have. You might say that you have a horizontal translation 2 units left. That's the terminology you might come across. A horizontal translation 2 units left. See how that kind of fits there? What about the plus 9? Now that I've shown you 1, how could they put that into vocabulary? That'll work, yeah. So that's the vocabulary you might come across too. 9 units. I guess, for sure. Okay, now one of the things that's interesting about translations is it really doesn't matter what sort of functions you're using. And so I've made a big list here of functions, and all of these are things that we'll do in this course. Some of them you might be familiar with, some you might not, but we can still write these equations of the new ones after we've moved stuff, even though you might not know all of these equations. Like, let me do one of them for you. I think you pick this up fast. What happens if I were to do this x plus 2 in place of x and then add 9? Well, then this guy would look like this. X plus 2, then square it, then add 9. Does that make sense? This x right here got replaced with x plus 2. Then I squared it because this one has to be squared, then add 9. So this next one here would be x plus 2, cube it, add 9. Okay, square roots. We haven't learned those ones, but how would this one work? Take a stab at it. Yeah. The x plus 2 still has to be under the square root sign. And then after you're done square rooting, then add 9. About 1 over x. 1 over x plus 2. X plus 2 is at the bottom. Add 9. Like, this skill can be extrapolated to any function, even if you don't even know what the heck the function means yet. This will be absolute value of x plus 2, then add 9. On this next half right here, I've got some functions that we're going to learn about. We haven't done all these yet, but I'm pretty sure you guys can figure out the pattern, right? 2 to the x plus 2, then add 9. What if there's more than one x? This goes where all of the x's are, and then when you're done, add 9. So this one's going to be x plus 2 squared plus 3x plus 2 plus 6, and then when you're done, add 9. On an example like this one, by the way, you could factor FOIL and do all that stuff, but we won't bother right now, but you could. Right? This would be sine of x plus 2, then add 9. So now for the really crazy one. Again, I'm just doing this to make a point here, right? It's going to be 4x plus 2 cubed plus sine of 4x plus 2 minus 4x plus 2 minus the absolute value of x plus 2. And when I'm done, hopefully this helps reinforce the point I need to make here, though. Do you guys feel like you get the difference between... Do you guys feel like you get the difference between inside a function and outside a function? Because the order really makes a difference, right? If I add $2 and then square it, it's very different than squaring it and then adding $2, right? So the easier one, almost always by far, is the just add 9 to the back, right? Because that one's just, oh, here, I'll just add 9, right? When you have to take like something like this and put it in there, you may have to replace that for all available x's. But this, I guarantee you, that happens once, right? The adding 9 you're doing once. This one right here, you have to replace all of the x's. So it can be a pain. What's up, Joe? I know it's all long. Awesome. Okay. We've actually kind of learned this before. Last year I would have shown you guys something called vertex form for quadratics. I don't know if you guys recall this, but we learned that the base of the quadratic is called the vertex. You guys remember this? And we can actually know where it is based on this format right here. Let me give you this example. I'm just gonna make one up here. Let's say I told you you had y equals 3x minus 1 squared plus 7. If you guys recall from last year, we knew that these 2 points right here were the vertex. The vertex was at 1 and 7. You guys remember this at all? Right? And so we actually kind of knew about this. The 7 means it went up by 7. The negative just meant it was the opposite. So if it's actually going this way, not that way, that's all. What does the 3 do, by the way? Right. And it helps with the slope or the. I mean, quadratics don't really have a slope in the same way. Sometimes we might use the word the nature or the inflection of the graph, perhaps, where the graph could be an upside down graph or a right side up graph. Okay, move on. Here's another task. I'm just trying to show you ways we can use this stuff now. Let's say I just gave you a random set of points. Could you tell me where the new points would end up at when we're done? So I'm just going to plot these ones first. Negative 2, 5 would have gone right here. 0, 0 would have gone here. 2, 4 would have gone right here. And 3, 2 would have gone here. If I just gave you random points, and I asked you to make these transformations to them, here's how it might look. What does the minus 2 mean? Okay, so over 2 and then plus 1, up 1. Over 2, up 1. Over 2, up 1. Over 2, up 1. There's my new points. So if I had to make a new table of values, if I were to ask you where the new points are for my new function, they'd now be at 0 with 6, right? Because negative 2 went to 0, 5 went up to 6. Then this would go over to 2 and up to 1. This would go 4 up to 5. And this would be 5 up to... Does that make sense what I did? Because really I took this number and I'm adding 2 to everything in this column. And then to everything in this column I'm adding 1 to it. So that's where these points have moved to. If my smartboard will let me, try this. Hopefully, I was hoping all 4 of these would go together as 1. If I could pick up all 4 of these points all together and move them over and up, they should be on top of each other. Okay, so that's another thing I need to be able to do, is they might show you an equation and ask you to work with it. They might give you a graph and ask you to work with it. They might just give you random points and ask you to work with it. All of those things need to be something you can do. Why don't I speed ahead, because I get the impression you guys are good at this. But if I were to ask you to draw me a graph, could you draw me what the new graph would look like if you were to subtract 1 here? I'll just do one of them real fast. Let me know if it doesn't make sense. You would do this. That's what the new graph would look like. Sweet, let's move on. Okay, more common example. This is something much similar to what you guys did on yesterday's quiz. Quadratic function has roots at negative 2 and 3, goes through the point 1, negative 12. I'm hoping right now alarm bells are going off going, hang on, why are they giving me a random point? Why am I giving a random point? So you can find that leading coefficient eventually, right? So, I mean, if it's a quadratic and it has roots, we already know that this can be x plus 2 and x minus 3. So far, so good. But we don't know the stupid leading coefficient, hence this is why they're giving me a point. So I'll plug 1s and negative 12s in everywhere. That'll give you 3, that'll give you minus 2, divided by minus 6 on both sides. Let me know if that blew too fast. You guys okay with that concept? Okay, well now we know our equation. Our equation is y equals 2 x plus 2 x minus 3. Now, it now wants to know what happens if it undergoes this transformation. Then it wants to know the new y-intercept. Okay, so let's talk this through here. What does this transformation right here mean? The whole graph gets moved to the left by 4 units. The whole graph got picked up and moved. So if I were to quick draw a picture of this in my head, it's going to have an intercept of, negative 2, positive 3. It had a positive leading coefficient, so it probably looked like this, right? This whole graph is now being asked to get moved that way by 4 units. what happens if I literally pick this thing up and move it over by 4 units? See how the y-intercept all of a sudden could be in a brand new place? Right? The y-intercept was down here. I mean, I'm just kind of guesstimating it. The y-intercept might have been, I don't even need to guess. What was the old y-intercept? 2 times 2 is 4 times minus 3. This y-intercept used to be minus 12. But as soon as I slide this graph over by 4 units, I mean, it depends on how far I slide it, right? If 4 units is like, say, this far over here, all of a sudden it's way the heck up here. How do I solve this? Well, here's another way of approaching this. What does fx plus 4 really mean? Well, it means take all of your old x's and replace them with x plus 4. So you know how I used to have an equation written right here? Here's my new equation. It's now g of x. Okay, 2 stays. Hey, I have an x. Okay, you're now x plus 4. All right, plus 2. Hey, I have an x. You're now x plus 4. Minus 3. See how I'm just replacing all the x's with x plus 4s? Okay, now I'll just clean it up a little bit. X plus 4 plus 2 really means you have x plus 6. And x plus 4 minus 3 really means you have x plus 1. So I'm just combining these like terms, right? This x turned into x plus 4, but the 2 had to stick around. This x turned into x plus 4. The 3 stuck around, but now I'm adding together my like terms. Okay, let's talk this through. This graph right here should now have a root of -6 and -1. I think that makes a ton of sense, though. Let me go back to this picture right here. Right here, these roots were supposed to be at, what was it, -3 and 2? If I slide this over 3 units, it's now at -6. That makes sense, right? If I slide this over 3 units, it's now at -1. That makes sense. Right? Where'd that y-intercept end up at? 2 times 6 times 1. If I don't foil the whole thing, right? But if I were to foil it out, what would the constant term have been? 2 times 6 times 1 would be 12. Does that make sense? I wouldn't foil the whole thing. That's a waste of your time. I would just focus on just the number coefficients, right? This 2 will eventually times by this new 6 you made, and that'll eventually times by that 1, and so it looks like my new y-intercept will be 12, which kind of makes sense. Like I can even see that in the picture. Doesn't this kind of feel like what we were kind of doing on yesterday's test there? Where it's, I mean, you have these skills, it's about piecing them together to solve the puzzle. Any questions? Okay, let's try another. Now that I've covered translations moving side to side, I want to try another concept here. Okay. I want to take a look at 2 different graphs right here. This one is x plus 1 that was supposed to be squared, and one of them has a negative sign in front of the entire thing. And then here's one right here where I'm going to have a negative sign, but it's only going to x. Okay. And I want to just graph these on a calculator here to get a sense of what's happening. So, if I could actually, I'm just going to start with this one right here. Can you guys graph, before we even do these 2 right here, can you graph x plus 1 squared? We'll just graph that one. What is this supposed to look like? Nice parabola that's been slided over 1. Exactly. Okay, now let's try this first one I have here. What if I were to take this function here and throw a negative sign in front of the whole thing? Yeah, that's what we're going to hopefully discover. Is here's the 2 graphs. Here's my parabola that's been slid over to the left. And look at that, now it's upside down. What happened? Well, this negative sign right here, hopefully you'd agree, it's outside the function, right? It's outside. I mean, the function itself is basically this whole thing right here, right? The function is that. And in front of it, I threw a negative sign. What happens when I do things outside of the functions? What does it affect? Up and down direction. It used to be positive. We've essentially now given it a negative leading coefficient, and we flipped it all upside down. All of your positives are now negative. All your negatives are now positive. So this flipped things head over heels. We call it a reflection. Well, now look at the other one we've got right here. Over here, I'm still going to apply a negative sign, but rather than applying the negative sign in front of the function, I'm going to apply it inside the function. See the difference between the in and the out? I'm going to throw the negative sign just directly in front of the x. Okay, here's my first function. Here's my one over there. What happened between those two? The first one flipped upside down. The second one flipped side by side. Use my same analogy of bringing money to the bank. You were going to bring positive money to the bank. But before you started, you decided to bring negative money instead. You know what I'm saying here? Like, it's like the robbing example, only you're bringing like positives and negative instead. All it does is it flips your x coordinates side by side. So if you kind of get these concepts, I'm going to move forward here. So we're getting towards the end of the day. Here's the words on this then. Let's say that you put a negative sign in front of the function, meaning that you apply the function, and then when you're done, make it negative. So if you had a positive, well, now it's negative. If you had a negative, now it's positive. All it does is it flips the graph head over heels, top to bottom. If you used to have a smiley face up here in this quadrant here, what would it look like now? With eyes underneath. Does that make sense? That's what would happen if you threw a negative f of x. These y outputs just become negative outputs. Or if they were negative, they become positive. Okay, here's a term that's going to come up. I guarantee it. It's called an invariant point. If you guys know English, you know what vary means, right? What does vary mean? No. Yeah, okay, that'll work. I get what you're saying. I was going to use the word to change. Right? Vary means to change things up, right? I'm going to vary my wardrobe today. I'm going to change it up, right? So if you have an invariant point, we're talking about points that don't change. Does that make sense? So let's say that you were to take a graph. I'm just going to draw one right here. And I were to flip it upside down. It now gets flipped to here. Which point doesn't move? Well, the one that's right on the axis. Does that make sense? Like, it's the only one that doesn't change. The one that's like literally on the plane of the mirror. If I were to have like another graph I'm just going to draw here, like say this one like this. If I were to flip it upside down and draw it like that, give or take, the point that doesn't move is the one that's directly on the axis. Fair enough? So that's a vertical. Horizontal then is when you flip it side to side. Here's where you put an x, but you make the number negative inside the function. Things inside the function affect things side to side. Things inside the function affect things side to side. Things outside the function affect them up and down. Abby, I like the way you do that. I'm going to steal that. So if this was your smiley face here, I even like the way you did that. I'm going to steal her idea. Then this one goes to there. Right? Where like this point hops to there, and this point hops to there. I really like that. Really, you get it. That makes sense to everybody? On this one here, then the invariant points are going to be on your y-axis. Okay, so let's try some more games and activities here. We'll just talk through some of these here. You can mark those ones, yeah. Is the key not on the board then? There's like 4 keys on there because of different classes. Take one while I look. I thought it was on there. If not, we'll get it later. Okay. How are these two graphs related here? The original one to the dotted one. If this graph right here is f of x, this graph right here is, maybe I'll just do the first one. Does that make sense? This one is f of negative x. It's flipping it side by side. You guys visualize that? Okay, I'll just do one more. This one over here, if this is h of x, then this one right here is negative h of x, because it's getting flipped up and down. This negative here is basically your leading coefficient, right? You're taking your leading coefficient and making it negative, which means the inflection's upside down now. Okay, let's try, what else should we do? Let's try this one here, and then I probably just have to finish tomorrow. Why don't we try drawing 1 or 2 of these ones? Okay, if I gave you this one right here, this was the original graph, and I said do negative f of x. What does the negative sign mean to do? My head over heels. Sometimes with my classes I find it's useful to use my hands, and so I might say we need to slide this way, or this way. Sometimes you need to flip this way, or this way. So sometimes it just helps to use your hands and say, flip it head over his. So if you wanted to sketch it, it would need to look something like that. You guys do like the mirror image by yourselves? I would just take a few key points and double check them. Like this one here is now there. This point didn't move, right? The one on the axis overlap. This one didn't move. This one didn't move. If you get the concept, let's move on. We'll do the last topic we've got, and then we'll call it a day. There's actually two more things we can do. There's a running tally, by the way. We've had like 1, 2, 3, 4. We're up to number 5. There's another thing you can do called a stretch. Okay, and it basically involves the same thing as like flipping does. You can take a graph and you can stretch it almost like it's getting pulled in both directions like this, or like this. You can have things go horizontally or vertically again. Jordy, can you do me a favor? Open that door for Jason. So without doing all of the like the preamble, like guessing and checking, let's just talk through the theory here. Let's say that I gave you y equals 2 f of x. You know what this is going to do is it's going to make your graph twice as big. Right? All of your y values are now going to be taller than they were before by twice as much. Let me just do a quick like picture graph here. Let's say that I gave you a graph that looked like let's say the graph looked like this. If I were to make it twice as tall, this would now be up there. You know what I'm saying here? Because this used to be that high, well now it's twice as tall. The same thing happens to negative numbers though, right? If I make, this was like say negative something, well now it just becomes twice as low. And so that's what this graph would do, is it's literally taking it, if you can imagine this, and like pulling it further up. That's what a 2 would do here, right? 2 would make everything twice as tall. Well, if you can expand things and make them taller, imagine like a trash compactor. Couldn't you take them and squish them in and go like this? All you've got to do here then is use y equals 1/2 f of x. What this does right here is it takes all your y values and makes them compressed towards the axis. So I want to try a picture here to kind of illustrate this one then. You guys remember what an absolute value function looks like? Like a v? Okay, so I'll use purple for a v. What's going to happen if I do -3 before? What's the negative do? A negative makes it go, if you're multiplying by -3, the negative flips it upside down, and the 3 makes it stretched taller. So watch this here. This point right here, if I make this, what's the output right here? Okay, so if I times it by 3, it's still right here. What's the output right here? Make it 3. Here it was 2. Make it 6. 3. Make it, no, I'm screwing this up here. I didn't draw that in the right spot. I'm trying to go too fast because I'm running out of time. What do I have? 5 minutes. Okay, let me do this better. Okay, 1 was supposed to be at 1. Now we'd make it up here to 3. But it's supposed to be negative, so let's put it down here at -3. Okay, I'll do them both at once. Here was an output of 2. Okay, well 2, if you triple it, should get you up here to 6. But then when you make it negative, it goes down here to -6. You guys see how what's happened to this graph here is it's gotten pulled taller, and then it's upside down. Sometimes I use an analogy of, you guys ever see like those fun houses where they have mirrors that make you look taller or shorter or thinner or fatter or something like that? This is a mirror that makes you look upside down and taller. Touche. Okay, let's try one last one here and then I'll have to start packing up, I think. What if I gave you 1/2 x? What's that going to do? Yeah, it's making you shorter. So here's what this will look like. it's actually going to look like this. You're still right side up, but all of these points are now half as tall as they used to be. See how that works? Your function is now 1/2 as big as it was. In a way, your y values are all 1/2 of what they were. Okay, why don't we call it a day there? Because I'm running out of time here. Let me just foreshadow what we're going to do tomorrow then. The last things we have to talk about are, well, if we can stretch things vertically, we should also be able to stretch them horizontally. Okay, and so we'll kind of go through that. And that's going to give us 6 things that we talk about. So if I can recap them all that we've done so far. We've got vertical translations, so moving the graph up or down. Add numbers, subtract numbers. Horizontal translations, move the graph side to side. We can also take a graph and reflect it head over heels. We can also reflect it side by side. The last things we can talk about are stretching it and like making things either taller or shorter. But if you make them taller or shorter, you should also be able to make them wider or thinner. So we'll do that. And then the last thing we need to talk about, and just have these notes ready to go here, is part 2 of this lesson, is what happens when we do them all at the same time. What if we do a stretch, a translation, and a reflection? We do a whole bunch of things at once. So my goal is eventually to be able to say, what's happening here? That's my goal here, is to be able to say, what does this 6 do? What does this 5 do? What does that 2 do? What does that negative do? We're going to put them all together. Kind of, yeah. Okay. Let's call it a day. We'll talk more tomorrow, guys.